Assalamualaikum. Salam sejahtera. My name is Fadila. My presentation today to computer intelligence. Number one, for the introduction data and problem. CDC Diabetes Health Indicator. CDC database health indicators is from a major public health survey. It continues various health indicators include data on choice, health condition, lifestyle choice, and preventive health practice among adults. The group project objective for introduction to dataset and problem, the goal is to utilize machine learning techniques to predict the risk of diabetes based on this health indicator, which can aid to easily diagnose and preventive healthcare strategies. For challenges identified, the main challenges identified addressing data imbalance, handling missing value, and ensure the model prediction are reliable and applicable to device populations. Number 2, justification of selected algorithm. MLP classifier. It is selected for this ability to model complex non-line relationships between many input, feature, and train models in real time online learning. This make them well suited for tasks with non-line decision boundaries or interact pattern. Logistic regressions. Chosen as a baseline model for the simplify and effectiveness in binary classifications problems. I can handle line relationships between feature and the log-on of the outcome. Logistic regression can be regular to avoid overfitting, enhance its performance on unsent data. Its competition less intensive make its good choice for problem with many feature easier to implement and interpret and very efficient to train. Number 3, development of solution step. Data pre-processing. The data is normalized to ensure the all feature contribute equally to the model's training process. Missing value are handled to maintain data integrity. Model training. This is for example to MLP classifier. The MLP classifier and logistic regression models are trained on the data set with careful hyperparameter tuning to optimize their performance. Next step, development of solution. Model evaluation. The model are evaluated using accurate, precise, recall, and ROC AUC score to assess their performance comprehensively. Thank you.
Hi everyone, in this session we dive into the critical process of parameter selection for our machine learning model. We will discuss the importance of parameter selection in machine learning model, the MLP classifier and logistic regression. Turning this parameter is essential to strike a balance between model complexity and performance. Comes to the MLP, multi-layer perceptron classifier, our focus is on fine-tuning several key parameters. These include 4 number of hidden layers, We carefully considered the architecture of our neural network. The number of hidden layers contributes significantly to the model ability to capture complex patterns in the data. Neuron per layer. Within each hidden layer, the number of neurons determines the capacity of the model to learn intricate relationship. Balancing this number crucial to prevent underfitting or overfitting. Activation function. We choose activation functions such as rectified linear unit to introduce non-linearity into the model. This non-linearity allows the network to learn from the complex data pattern. The objective is to find configuration that captures the underlying pattern in the data without introducing unnecessary complexity. We choose logistic regression. Shifting our focus to logistic regression, our attention turns to hyperparameters that influence the regularization and generalizability of the model. Regularization strength. Logistics regression includes regularization terms to prevent overfitting. The regularization strength parameter control the impacts of the regularization on the model. The higher C value reduce regularization while a lower one increase it. Other hyperparameter, depending on the implementation, there may be additional hyperparameter to consider, such as the choice of solver of optimization and tolerance values. The goal here is to find the right balance, applying regularization to prevent overfitting while allowing the model to generalize well to new unseen data. Others parameter we choose a significance. Tuning this parameter is not a one size fit all task. It requires a careful examination of our data set, understanding the complexities within, and adjusting the model parameter accordingly. Achieving the right balance ensure that our model are not too simplistic, risking underfitting, not overly complex, leading to overfitting. In conclusion, parameter selection is a crucial step in the model development process. The choice we make impact the model ability to generalize and make accurate prediction. The result discussion segment. Let's dive into the performance analysis of our model, the MLP multi-layer perceptron classifier and logistic regression on predicting the risk of diabetes using the BRFSS 2015 dataset. Beginning with the performance analysis, we observe that the MLP classifier demonstrates a remarkable level of accuracy. This indicates that the model has effectively learned from the training data and performance well on the test set. However, a point to note is potential susceptibility to overfitting. High accuracy of MLP classifier. The model achieved a high degree accuracy, suggesting that it accurately predicts diabetes risk based on the diverse set of health indicators in our dataset. Concerned about overfitting, while the high accuracy is promising, we need to be cautious about overfitting. The model might have become too tailored to the training data, potentially affecting its performance on new, unseen data. In contrast, logistic regression represents a more balanced performance. Let's explore why. Balanced performance of logistic regression. Logistic regression, known for its complicity, showcase a balanced performance. It avoids the complexity that could lead to overfitting, making a robust choice for our predictive tasks. Moving on to insight and implication, the result will be obtained underscore the immense potential of machine learning in the realm of predictive healthcare. Identification of high-risk individuals. Both models provide valuable insight into identifying individuals at high risk of diabetes. This capability opens avenue for early intervention and preventive healthcare strategies. Machine learning in the predictive healthcare. The success of our model highlight the power of machine learning in leveraging diverse health indicators. For predictive analytics, this has significant implications for improving healthcare outcome by identifying potential health risks before they escalate. In conclusion, while the MLP classifier excels in accuracy, consideration regarding overfitting prompt us to carefully evaluate its performance on new data. Logistic regression, with its balanced performance, emerged as a reliable option for our predictive healthcare tasks. The insight gained from our model, the way for proactive healthcare measures, showcasing the potential impact of machine learning, enhancing early diagnosis and intervention. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Azizah Abdullah. I will explain about source code process workflow. It contains 5 steps. Number 1 is loading data set. Number 2 is data processing. Number 3 is model training. Number 4 is model evaluation. And number 5 is high risk profile prediction. So we go for number 1, which is loading the data set. The data set is from Excel file, and it will use pandas library to get the data set for the analysis. This is the data set of CDC diabetic health indicator that has been used for this project, and it contains the variable tables with the scale for each table. The scale for each table will give a meaning, and all the data set inside here will be go through the 5 process to get the result, which is to use the 2 algorithm that have been we choose, is the MLP classifier and also the logistic regression. For step number 2 is the data processing. Inside the code, we use the standard scaler, which is for scaling features and handling the missing value. Our data is a supervised data, and the pre-processing stage ensures the data is in a format suitable for model training, enhancing the model ability to learn from the data. The third step of source code process workflow is a model training. It will use code snippet to initialize the MLP classifier and logistic regression and feed them to the training data. The training involves adjusting the model's parameter to learn from the dataset pattern, which the code snippet are small block of reusable code that you can add to a code file. Step number 4 is a model evaluation. The model are evaluated on the test set using metric like accuracy and ROC-AUC. This metric provide insight into how well the model can generalize to new and unseen data. And the last process is the high risk profile prediction. The models predict the risk category for a predefined high risk profile. These steps test the model ability to identify high risk cases accurately. This is a process flowchart from the beginning. If we go to step number 1 is load dataset. The dataset is from excel.csv. After that, we go to second step, which is the data processing. Inside the data processing, we have 3 segments. For normalized data, it will go to scale data. For the missing value data, it will go to input or remove missing data. And then segment number 3 is split into train and test. After the data go through either one of these, it will go to the third step, which is the model training. Inside the model training, we have 2 algorithms to train the data, which is the train MLP classifier and train logistic regression. After that, it will go to step number 4, which is the evaluation model. Inside the evaluation model, we have also 3 segments to calculate accuracy, precision, recall, and F1 score. And segment number 2 is generate confusion matrix, and number 3 is a compute ROC-AUC score. After that, it will go to compare model performance, and then the data will go into select best performing model and apply model for prediction. After that, the process is end, and we can get the result. The procedure code for this project, we have 5 elements. The number 1 is load data, which is the load data is to read the data set using pandas. Number 2 is a pre-processed data to check the normalized features, handle missing value, and split the data set. Number 3 is the train model to initialize and train the MLP classifier and logistic relation on the training data. Number 4 is to evaluate model, which to use the accuracy, precision, recall, and ROC-AUC to assess the model performance. And lastly, the procedure code is predict high risk profile, which to use the trained models to predict the risk category of the predefined high risk profile.
Today, I'll be walking you through our project, which focuses on predicting diabetes risk using machine learning techniques, specifically utilizing the BRF-SS 2015 datasheet. The datasheet contains around 22 columns, which one of them is used as the target variable, which is column diabetes_012. 0 means that the patient is not diabetic. 1 means that the patient is pre-diabetic, and 3 means that the patient is diabetic. Loading the dataset. Let's start with how we load our dataset. We use the pandas library, a powerful tool in Python for data manipulation, with just one line of code, which is pd.read_csv. We can load our entire dataset for analysis. Data preprocessing is crucial. We first scale our features using standard scaler to ensure our model treats all features equally. Then, we split our data into training and testing sets, which is essential for evaluating our model's performance on unseen data. Here, we define our multi-layer perceptron classifier. This model is a type of neural network known for its effectiveness in classification tasks. We specify the architecture and the number of iterations for training. In parallel, we use logistic regression as our baseline model. It's simpler compared to MLP, but highly effective in binary classification tasks. The max_iter parameter defines the maximum number of iterations for the model to converge. Once our models are trained, we evaluate them using accuracy and ROC-AUC scores. These metrics help us understand not just how often the model is correct, but also how well it distinguishes between classes. Finally, we test our model's ability to predict high-risk profiles. This step is vital for assessing how well our model can identify individuals at high risk for diabetes, which is key for preventive healthcare. In conclusion, our project demonstrates the power of machine learning in healthcare analytics. By leveraging the BRF-SS 2015 datasheet, we've developed a tool that can aid in early diagnosis and intervention for diabetes.